Dear students, good day for you. And I am Dr. R. S. Ramkumar, Head and Assistant Professor of Department of Mathematics and Self-Finance Stream at Sri SNM College, Satur. Today we are going to see about the basic definitions of a graph and types of graphs in a graph theory. So first we will see the definition of a graph. A graph is an ordered triple. G is equal to V of G, E of G and Ig. Here V of G is a non-empty set. So this one is a vertex set. To form a graph, first thing we need is points. So without points we cannot draw a graph. So first we need a collection of all points. So this one is called a vertex set V of G, and the next one is a edge set of G, so which is disjoint from the V of G. So edge set is nothing but it's a lines or arcs. So to join 2 points we need lines or arcs. So these collections is called the edge set of G. Next one is the incidence function. So there are 10 vertices in a graph. Which two of the vertices are connected by the edge E? So this relation is mentioned by the incidence relation, and the elements of V of G are called the vertices or nodes or points of G, and the elements of V of G are called the edges or lines of G. V of G and E of G are vertex set and edge set of G respectively. We write Ig of E is equal to set of all UV. That means to form a edge E, we can connect the vertices U and V. So simply we write Ig of E is equal to UV. So in that example, for a graph G, the vertex set V of G contains the 5 vertices V1, V2, V3, V4, V5, and the edge set of G contains the 6 edges E1, E2, E3, E4, E5, E6, and the incidence relation for E1 is E1 is obtained by the connecting the vertices V1 and V5. So like that, E2 can be formed by connecting V2 and V3, and by connecting V2 and V5 we can form the 2 edges E4 and E5. So like that, the incidence relation of the edge 6 is by connecting the V3 to itself. So here there are different kinds of edges. There must be the one edge between the 2 vertices, and one more edges between the 2 vertices V2 and V5, and single edge from the vertex to itself also here. So next one, if the incidence function Ig of E is equal to set of all UV, then the vertices U and V are called the end vertices or the ends of the edge E. Here the each edge is said to join its ends. We say that E is incident with the each one of its ends, and also the vertices U and V are incident with E. So here the edge E can be formed by the vertices U and V. Then we can use the word incidence. So for example, so in that figure, E1 is incident with V1 or V5. So here there are 2 parameters, the edges and vertices, and the edge should be incident with the vertex. So by using the term incidence, we can mention E1 is incident with V1 and E1 is incident with V5. Here E6 is incident with V3. Next one, multiple edges or parallel edges. A set of 2 or more edges of a graph is said to be a multiple edges or parallel edges if they have the same pair of distinct ends. That is, by using the 2 vertices we can form more than one edges, then it is called parallel edges or multiple edges. So in that example, by using the vertices V2 and V5, we can form the edges E4 and E5. Here E4 and E5 are called the parallel edges or multiple edges. So if E is an edge with end vertices U and V, then we can write E is equal to UV. So this one is a notation for the edge E in terms of the vertices U and V. An edge for which the two ends are same is called a loop at the common vertex. So in that example, by using V32 itself, we can form the edge 6. So this one is called a loop. Next one is a neighbor of a vertex U, of a vertex V. So a vertex U is a neighbor of a vertex V in G if UV is an edge of G and U is not equal to V. So for different vertices U and V, there must be an edge between these two vertices U and V. Then V is a neighbor of U. U is a neighbor of V. The set of all neighbors of V is the open neighborhood of V or the neighbor set of V, and it is denoted by n of V. So just by collecting all the neighbors of the vertex V, we give the notation n of V. The set is called the neighbor set of the given vertex V. The n of square bracket of V is equal to n of V union singleton V. So by taking that vertex V into the neighbor set, then this neighborhood is called the closed neighborhood of a vertex V in G. So we have a different notation for the open and closed neighborhoods. And next one is, we have already seen the incident of a edge to the vertex. Now the parameters are same. If you consider two vertices or if you consider the two edges, then we can use the term adjacent. The vertices U and V are adjacent to each other in G if and only if there is an edge G with U and V as its ends. So in between U and V there is an edge, then U and V are adjacent. Like that, two distinct edges E and F are said to be adjacent if and only if they have a common end vertex. So in that example, here V1 and V5 are adjacent because of V1 and V5 are connected by the edge E1. Like that, E1 and E4 are adjacent. To these two edges are adjacent because of they have a common vertex V5. Next, a simple graph. A graph is said to be simple if it has no loops and no multiple edges. That is, for a simple graph G, the incidence function is 1, 1. This must be the one-known function. So we consider the ordered pair for a simple graph V of G and E of G only. So in that example, it is not a simple graph because of it has a multiple edges and loops. These are all the other examples. So in the first diagram, E1 is a loop and E2 and E3 is a set of multiple edges. Second graph is a simple graph because of it has no parallel edges and loops. Third one is a labeled or unlabeled graph. That means we give a name for each and every vertex. So in the first graph G, the vertices V1, V2, V3, V4 are mentioned. But in the second graph H, there are no symbols. So if we mention the symbols, then a graph is said to be a labeled graph, or otherwise it is unlabeled graph. So this one is a proper definition. A graph is said to be labeled if its n vertices are distinguished from one another by labels such as V1, V2, Vn. These the first three graphs are the different one because of V1 and V3 are not adjacent in the first graph, but V2 and V3 are adjacent in the second graph. So even though V1, V2 and V3 are connected in the third graph, V1 and V2 is not adjacent in the third graph. That is, the first three graphs are different from one another. Next one is a simple graphs and isomorphism. If you consider two graphs, two simple graphs G and H, now by defining the bijection map from the vertex set of the first graph G and the vertex set of the second graph H, such that if U and V are adjacent in G, if and only if these images pi of U and pi of V are adjacent in H, that induces a bijection theta E of edge set of G to edge set of H, satisfying the condition that if the edge E can be formed by connecting U and V in a graph G, if and only if, then the image of the edge E under theta, that means theta of G, theta of E in H can be formed by connecting the pi of U and pi of V, the images of U and V. Hence, pi itself is an isomorphism in the case of simple graph G and H. Thus, if G and H are simple graphs, an isomorphism from G to H is a bijection from V of G to V of H, such that U and V are adjacent in G, if and only if, then their images pi of V, pi of U and pi of V are adjacent in H. The next one, this one is an example for the isomorphic graphs. So here, the image of U1 is V1, the image of U2 is V2, like that. The image of UI is Vi. So here U1 and U2 are adjacent, then the image pi of U1 is V1 and pi of U2 is V2. So V1 and V2 are adjacent. So that means pi of U1 and pi of U2 are adjacent. So like that we can check all the vertices of the Petersen graph P and their corresponding image graph. These two graphs are isomorphic graphs. Next one, a simple graph is said to be complete if any pair of distinct vertices of G are adjacent in G. So, from this we can conclude any two complete graphs each on a set of n vertices are isomorphic, and the complete graph is denoted by K suffix n. So, for the example K1, so it contains only one vertex, and K2, so there are two vertices in K2, and these two are connected by a single edge, and K3, it contains three vertices and all the vertices are connected. This one is K4 and K5. Next one is a bipartite graph. A graph is trivial if its vertex is a singleton and it contains no edges. A graph contains a single vertex, then it is called a trivial graph. The next one, a graph is said to be bipartite if its vertex set can be partitioned into two non-empty sets X and Y, such that each edge of G has one end in X and one end in Y. The pair X comma Y is called the bipartisan of a bipartite graph, and it is denoted by G of X comma Y with a bipartisan X comma Y. So, for a given set of vertices, just split the vertices into two sets X and Y and make the adjacency to the one set to the vertices of one set to the another set. So, do not make the adjacency between the same set. So, here in the first example, a bipartite graph, you can see adjacency between the vertices are made by the vertices of X to Y. So, not into the vertex itself. Then if each vertex of X is adjacent to all the vertices of Y, then the graph is said to be a complete bipartite graph. So, it is denoted by K, P, comma, Q. So, cardinality of X is equal to P, cardinality of Y is equal to Q, and the complete bipartite graph is denoted by K, P, comma, Q. The second one is K2, 2, comma, 3. So, this one is a complete bipartite graph. The first set contains two vertices and the second set contains three vertices, and all the vertices of the different set are connected by the edges. A complete bipartite graph of the form K1 comma Q. That means the first set contains only one vertex and the second set contains Q vertices, and make the adjacency between the vertices of one to the another set, we can get a graph. This graph is called a star graph. GBA graph, simple graph. The complement of a graph is denoted by G complement. By taking vertex set of G complement is equal to vertex set of G. There is no changes in the vertex set, but making two vertices U and V are adjacent in G complement if and only if they are non-adjacent in G. So if U and V are adjacent in G, then U and V are adjacent in G complement, then these must be non-adjacent in G. So from that we can deduce cardinality of V of G is equal to N, then cardinality of edge set of G plus cardinality of edge set of G complement is equal to cardinality of edge set of the complete graph Kn. So which is equal to n into n minus 1 by 2. So there are n vertices, and by using two vertices we can form a single edge. So NC2 value, therefore n into n minus 1 divided by 2. These are all the examples for G and G complement. So for the first graph G, we can form the G complement. So in the first graph U1 and U3, in the first graph U1 and U3 are not adjacent, but in the G complement U1 U3 are adjacent. So in H, U1 and U4 are not adjacent. So in H complement U1 and U4 are adjacent. Next one is a self-complementary graph. So if G is isomorphic to G complement, then a simple graph G is said to be self-complementary. These are the example. Here the first graph contains 4 vertices. So if you form a G complement, then G and G complement are isomorphic. So like that in the second example, there are 5 vertices. So if you form a G complement, then G and G complement are isomorphic. So these are all the examples for a self-complementary graph.